Hi everybody, welcome back. So for this lesson we're going to be talking about the derivative of a function. Now I want you to recall what we were looking at for the previous section when we were looking at the tangent line to a given curve. We were able to extract the slope of that tangent line to the given function f of x at some value, at some point value p. So in that particular case, we were then able to extract that f prime at a was equivalent to the slope that we were observing for the slope of the tangent line of that given function. Now, in this particular lesson, we're going to keep elaborating on that. And the way we're going to keep elaborating on that is that now we want to look a little bit further and we want to start extracting what is a derivative. So for this portion, we have that the derivative of a function f at a point a, denoted by f prime at a, is this given function. Now, this given function is still the exact same function that we were working with in the previous section. It's still the slope of the tangent line for the given function f of x at a point, in this particular case, value of a. And this has to work provided the limit exists. So in general, if we want to find a general derivative, or let's say a general formula for the derivative of a function, then instead of substituting a value of a, we'll just leave it in a general sense in terms of x. Now, more specifically, we also want to look at that the derivative of a function at a point gives the slope of the tangent line at that point. And that was the previous section. That is what we were working on previously. But for now, for the first example, we want to find a formula for the derivative of this function. Now again, in order to find this formula, we have to stick to the definitions that we're using. So again, there's two different definitions that you can use. Number one, you can work with the difference quotient and then take that limit. Or number two, we can work with the average rate of change and we can take the limit of that function. And again, whichever one we want to use, it should lead us to the exact same answer. So if we're looking for f prime of x, so f prime of x, we're going to be looking here for the limit as h is approaching 0, and this is going to be for f of x plus h minus f of x all divided by h. And if we go ahead and make our substitutions, f of x plus h, this gets me 80 times x plus h minus 6 times x plus h squared, and then we do minus my f of x value, which is 80x minus 6x squared. All of this is divided by h. And again, we can go through the highlighting piece. That this piece that I'm highlighting here is my function f of x, and my first term here, or my first terms, belong to the quantity of f of x plus h. Now all we have to do is just keep expanding this, and that's exactly what we're going to do. We're going to keep going here, that the limit as h is approaching 0, distribute, we're going to get 80x plus 80h minus, I'm going to expand this and distribute the negative 6, so that's going to be negative 6x squared minus 12xh minus 6h squared. Okay, that was my first terms. And then minus 80x plus 6x squared, all divided by h. And again, my first terms are here. second terms are here. And again, I distributed that negative. So now what I get to do is I get to simplify certain terms. I have an 80x, it simplifies with negative 80x, they cancel. I have a negative 6x squared and I have a positive 6x squared, they cancel, which means we're only left with 80h minus 12xh minus 6h squared, all divided by h. So now notice every single term has an h, which means we can factor and simplify every single term that has that h, and we're left with 80h minus 12x minus 6h. Now when we take the limit here, as h is going to approach 0, then this last term will be approaching 0. In other words, we're only left with 80 minus 12x. And this is my formula for my derivative for my function f of x. Now again, we're not identifying at a specific point. If we identified at a specific point, we can make that substitution at this point in time and everything would be hunky-dory. Awesome. So again, now that we have this, let's keep going. Let's keep going with this whole process. So for my example here, we're going to have that if g of t is equal to 1 over the square root of t, we want to find g prime at t, and again using the limit definition. So again, we're going to start off by interpreting that limit definition. So if I'm looking for g prime of t, this is going to be the limit as h is approaching 0 for your function g of t plus h minus g of t, all divided by h. So as h is approaching 0, we're going to make our substitutions. My function g of t, this is going to be 1 over the square root of t plus h minus g of t, which was 1 over square root of t, all divided by h. And again, g of t is that specific term. G of t plus h is this first term that we're looking at here. Great. Now, in order to simplify this, what I'm going to do is I'm going to multiply both numerator and denominator by square root of t multiplied by square root of t plus h. There we are, just like that. Okay, so multiplying both numerator and denominator by those specific factors will then be able to simplify my complex fraction. So as I distribute to my first term, the t plus square root of t plus h is going to cancel, and we're going to be left with the square root of t. The second term, when we distribute, will cancel the square root of t's and will leave us with square root of t plus h divided by my denominator. And again, every time that I multiply, I don't want to distribute, or I don't want to actually multiply them out. I just want to signify that we are multiplying them. And so again, we still have our first term, that was our term here multiplied by these functions, and we have our second term here that was multiplied by this LCD. Perfect. So what I want to do at this point in time is let's try to find out, can we still substitute in h? Well, we can't take the limit of h because if we do try to take the limit, we're left with 0 divided by 0, which is indeterminate form. Instead, what we want to do at this point in time is we want to actually rationalize the numerator. So rationalizing the numerator, that's what I want to do here. I'm going to multiply by its conjugate, square root of t plus square root of t plus h, both numerator and denominator. As such. And when this happens, for my numerator, it's the difference of squares, which means we're going to be left with t minus t plus h, all divided by, and again, I don't want to distribute, I want to keep everything as is, square root of t plus h, multiplied by the square root of t plus the square root of t plus h, as such. Now, let's simplify a little bit. The numerator simplifies to just be negative h. Denominator is h multiplied by the square root of t, multiplied by the square root of t plus h, multiplied by the square root of t plus the square root of t plus h. And then notice the h factors will be able to simplify in the numerator and in the denominator, which means we're left with this really nice limit here that we can evaluate. Whoops. Negative 1 divided by square root of t times the square root of t plus h, multiplied by square root of t plus square root of t plus h. And as we take the limit as h goes to 0, well, taking that limit as h goes to 0, we're now going to be left with negative 1 divided by square root of t multiplied by square root of t, because again, plus 0, multiplied by square root of t plus square root of t. Wow, that is pretty cool. Let's keep going. So negative 1 divided by, and here I have the square root of t squared multiplied by 2 square root of t. Look at that. It's looking pretty good. Well, if we multiply everything here, we get negative 1 over 2 multiplied by the square root of t to the power of 3. In other words, this simplifies to negative 1 over 2 times t to the power of 3/2. And this is your g prime of t. So again, once we did all the work, we're able to find that g prime of t is equal to negative 1 divided by 2 times t to the power of 3/2. Really, really nice. So again, all of this is looking real good as long as we're using that definition. Chances are you want to keep using this difference quotient definition simply because it'll make all of these, let's say, derivatives be kind of straightforward. Now, we do have alternate notations for derivatives. So we're going to go through those alternative notations. So we're going to have these alternative notations for these derivatives. Well, we're going to have what we've been working with, f prime at x, and this is going to equal, well, if we're given a function that's y is equal to f of x, well then this is going to be equal to just y prime. This is also going to be equal to the derivative of the function y with respect to x, also equivalent to the derivative of the function f with respect to x. We can write this as the derivative with respect to x for the function f of x. We can write it as the derivative, capital D, of f of x. Or we can write it as the derivative with respect to x for our function f of x. So again, we have all of these different notations. And all of these different notations are not here to confuse you. Instead, all of these notations came about from the mathematicians that were initially discovering them. Newton was one of the mathematicians that was credited with discovering calculus. Notice I said one, because apparently there is a big feud in the mathematics community as to who invented calculus. If you ask me, it was neither. So, here we have Newton. Newton started working with derivatives, and he invented this notation that we eventually came to extract as f prime or y prime. And the way he was using this notation was more specifically looking at y and just putting a dot right above it. That signifies that we were looking at a derivative of that function. Now, Leibniz was the other mathematician. They both developed calculus independent of one another. So again, they were not working with each other when they were trying to prove these results or analyzing these results. So Leibniz started using this notation that was dy dx. In other words, the derivative of y with respect to dx. And therefore we get these different notations in calculus that come about for these derivatives. Specifically because, again, two different mathematicians in two different places started developing calculus at the exact same time. And therefore they started developing their own notation, and naturally both of their works were accepted, hence we have two different notations. So again, we must be accustomed to working with these notations, and we must always keep them in mind. And as we work through this class or through this course, I'm going to be using an array of different derivative notations, and they're all going to be just listed here. So you'll see me cycle through f prime, y prime, dy dx, df dx, d dx of f of x, or d sub x of f of x. You're going to see me cycle through all those derivatives. That's just to make sure that you get the exposure to identify that we can express the notation for these derivatives differently. Now, what about taking higher order derivatives? In other words, can we take a second derivative? Can we take a third derivative, a fourth derivative, a fifth derivative? Well, the answer to that is yes. Yes, we can. And for that, we'll go ahead and we'll list it here, that we can take higher order derivatives. So higher order derivatives. And these higher order derivatives, if we start off with a function y is equal to f of x, then when I look at my first derivative, then we get, in this case, y prime, or f prime of x, or we just get dy dx. Now, what if I take my second derivative? Well, the second derivative is going to be denoted as y double prime, or in other words, f double prime of x, or using Leibniz notation, we can say the derivative that was taken twice of the function y with respect to x both times. So again, the respect was here for the x value. We typically call this f double prime in order to find that second derivative because we analyze the second derivative quite a lot. Then we have the third derivative. The third derivative, as you might expect, might be y triple prime is equal to f triple prime of x. This can also be written as the third derivative for the function with respect to x 3 times. Now, aside from this, the first 3 derivatives of a function, we just use this prime notation. Notice I've been referencing y prime, that's the first derivative, y double prime, that's the second derivative, y triple prime, the third derivative. The fourth derivative no longer has prime. The fourth derivative now has an exponent with a parenthesis. So be very, very careful when we're looking at these functions and we see an exponent with a parenthesis. If we ever see that, they are signifying that we are taking the fourth derivative. Okay, that means that we took the derivative 4 times for the function y with respect to x all 4 times. So again, once we get past that third derivative, we then just start simplifying and start writing out which derivative it is that we're looking at. Is it the fourth, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, whatever it may be. We can take the 99th derivative if we wanted to. Okay, so now that we have this notation for derivatives and these higher order derivatives, let's go ahead and let's state a theorem. This is going to be a theorem that we're going to be working with. So this theorem, I'll write on the right hand side of the screen, that way I won't have to scroll down. So here goes my theorem. Again, this theorem is going to help us out with what it is that we're looking at for derivatives. So if we have a function f and this function is differentiable, meaning we can take the derivative. So if f is differentiable at a, so if we can take the derivative at a, then the function f is continuous at a. Wow, that's awesome. And again, that's really awesome because now this is building upon the work that we were initially looking at before. Now, the work that we were looking at before, well, we were saying what is a function and when is it continuous, and we were able to use a limit definition to extract that a function was continuous at a given point if the limit exists for the function as x is approaching a and if it's equal to f of a. This theorem then says, well, if you identify that your function is differentiable at the point a, then you must be continuous at a. However, you must be very, very careful. If a function is continuous at a, it does not mean that it is differentiable at a. In other words, the converse of this statement is not true. And more specifically, we want to make sure that when we take derivatives, we have a smooth and continuous function. So I'm going to write here, when taking derivatives, we must ensure that the function is smooth and continuous. Now, what does this whole concept of smooth and continuous imply? Well, we have to make sure that there are no discontinuities. So no discontinuities is number one. No corners. Oops. We want to make sure that we have no corners or cusps. And then lastly, no vertical tangents. So if we do this, again, we have to make sure that our function is not only smooth and continuous, but we must also make sure that all of these items are being satisfied. Again, no discontinuities, no corners or cusps, no vertical tangents. So what does that mean for us? Well, let's check this out. I will give you a few examples as to what it is that we want to stay away from. Oops. Okay. Here we go. What I'll do is I'll copy this axis here. Once I label it, so we're going to have y's and we're going to have x's. So let's go ahead and let's copy this over. I want that here. There we go. And let's get another one over here. Perfect. There we go, it's looking good. And let's get this last one over here. Great. Okay, so what we're looking for here is, number one, we want to make sure that there are no cusps. So what does a cusp look like? Well, a cusp is going to be a value of a function that looks like this. This here is a cusp or a corner. And this is bad when we're taking derivatives. Okay, so we want to make sure that whatever function we're differentiating, it doesn't have this cusp or this corner. Okay, so again, this is bad for differentiation. And all of these are bad for differentiation, by the way. So another one that would be bad for differentiation would be discontinuities. So in other words, if we have a function that is not continuous, this is bad, again, for differentiation at the value of a. And so again, this is discontinuity. And the last one's a vertical tangent. So if we have a vertical tangent, say we had a function like this, if we had a vertical tangent could exist at this function at some given value of a. If we have a vertical tangent, again, this process for differentiation is pretty bad and we cannot take that into account. So that's a vertical tangent. We just have to make sure that we restrict the domain or we exclude that point from when we're taking all these derivatives. So these are the different items, or these are the different versions that we want to avoid when we're taking these derivatives. And that's why we want to make sure that our functions are continuous and they are smooth and they avoid these vertical tangents. So next, let's see if we can start applying some of these derivatives and higher order derivatives. So we get if f of x is equal to 5x squared plus 2x, we want to find f double prime at x, and this is a question. Alright, so let's go ahead and let's take this derivative then. Now, in order to get to the second derivative, we're going to go through and we're going to take the first derivative. So in other words, if we're looking at f prime of x, this is going to be the limit as h is approaching 0 for my function f of x plus h. So let's start with that substitution. F of x plus h plus 2 times x plus h minus my function itself, 5x squared plus 2x, all divided by h. And let's expand everything. Let's distribute and expand. So my first term here is going to be 5x squared plus 10xh plus 5h squared plus 2x plus 2h minus 5x squared minus 2x, all divided by h. And again, as you'll be able to see, some of these terms will be able to simplify, which is always good. More importantly, once they simplify, every single term on that numerator will have an h as a part of their factor, which means all of those factors, or at least a factor of h, will be able to simplify with one of the h's down below. So we then have 10x plus 5h plus 2. And as h approaches 0, well then naturally we're going to be left with 10x plus 2. And this is my derivative. This is f prime of x. Now remember, we want to find f double prime, which means we need to find the second derivative. So in order to find the second derivative, I'm going to use the derivative that I just found. So finding the second derivative will imply that I need to use the limit as h is approaching 0 for the derivative function of f of x plus h minus f prime at x, all divided by h. And so using this definition once again, I'm going to make my substitutions. Using my function f prime as my function that I'm making my substitution, I'm going to have 10 times x plus h plus 2 minus 10x plus 2, all divided by h. This will give me here the limit as h is approaching 0. Distribute, that's 10x plus 10h plus 2 minus 10x minus 2, all divided by h. As you can see, 2's cancel, 10x's, they cancel. 10h divided by h, it's just the limit as h is approaching 0 for 10. Limit of a constant, it's just the constant itself. Which means my second derivative is actually a constant and it's going to be equal to 10. So that's pretty cool. Alright, so I like that so far. Now, again, if I ask you to find the second derivative using the limit definition, then you have to go through this whole process to show that you found the derivative using this limit definition. Keep that in mind. Now, let's start off by looking at this here. Suppose that s is equal to f of t. And this is a position function where s is in feet and t is in seconds. Okay, so we have this in mind. Now, in order to extract this just a little bit more, I want to kind of give you a a graph per se. Okay. Let's see this graph. All right, here we go. Got that locked. Perfect. All right. And then I want to copy this down, that way I don't have to keep generating this over and over and over again. Okay, awesome. So I'll copy this, there we go. Okay, now just really quickly I'm going to erase this here because they told me that my function f of t is given by t, that's my independent variable, so that's my t-axis down here. Oh my goodness, look at that, it's zoomed out. Technical difficulties. Bear with me, everybody. Here we go. There we are. All right, there we go. Problem solved. Crisis averted. Let's keep going. Okay, so my independent variable here is my t values, so that's my t-axis, and my my vertical values here is going to be s, which is going to be in feet. And so, in other words, this is my f of t. So this is my f of t function. Now, I want you to then analyze all of this. So the unit of measurement for s is going to be in feet. So as I'm working with this, my unit of measurement for my y values are feet, and then my t values are seconds. So if I find an average rate of change, then that means I'm going to be looking at the change in y over the change in x. In other words, finding the change in y over the change in x, unit-wise, this is going to give me feet divided by the units that are going to be in seconds. In other words, this gives me a unit of measurement of feet per second. So if my function is a position function where the independent variable is t, in this case time, and the output is feet, well then my slope, or in this case my rate of change, is f of t. But remember what rate of change is. According to what we were looking at, rate of change is just a derivative. In other words, when we take our first derivative, s of t, this is going to give us a velocity, v of t. So we get this velocity. And the units of measurement so the units, they're going to be feet per second in this particular case, because again, they're telling us t is measured in seconds and s is in feet. It might be something else for, let's say, a different question. They might say t is in hours and your distance is going to be in miles. Hence, your velocity will be in miles per hour. Or if we were in Europe, it might be kilometers per hour. So we have to be able to make that distinction. Now for the second one, okay, and remember I said I was going to copy that, so here it is. Perfect. So again, I'm going to be using my t as my independent variable, but now my y-axis, or my vertical axis, I'm no longer going to be using this as feet. Instead, I'm going to be using this as s prime, in other words, f of t prime. Well, that unit of measurement, as we came to find out, that unit of measurement was feet per seconds. But time was still seconds. So if I want to find the rate of change of my, let's say, y prime here, divided by the change in my x values, or change in my t values, this is now going to be feet per second divided by seconds. In other words, this gets me a unit of measurement of feet per second squared. This is what we call acceleration. So anytime that we take a second derivative from our position function, we're then left with the derivative of the velocity, which is our acceleration function. And again, this is acceleration. And the units, they're going to be feet per second squared. Now, acceleration typically is denoted by your gravity constant close to Earth's surface, because as your gravity constant close to Earth's surface, you have that it should be about 32 feet per second squared. So here we get a natural extraction for what the velocity and what the acceleration is based upon what our initial function we were observing. And we have one more that we talk about, but a lot of people don't like to talk about this. It's a third derivative. A lot of people don't know that it exists. I do. And I like it. J of t. And a lot of people don't like to talk about it because this is the jerk. I know. It's so weird. It is an actual unit that we look at, and this is feet per second cubed. So, we do actually get to observe the jerk here, and the jerk is just going to be the derivative of the acceleration. And again, as we start looking at all of these examples and all of these, let's say, derivatives, we then have to start anticipating what does the first derivative tell us, what does the second derivative tell us, what does the third derivative tell us. Typically, the third derivative we want to stay away from because you want to stay away from jerks at all times, right? So, sorry, that's a small math joke. So, this is what we are observing at this point in time, and we typically only work with position, velocity, and acceleration. Okay, so I hope you all enjoyed this lesson, and for the next lesson we're going to be talking more about derivatives and more along the lines of their derivatives and their properties. Okay, so we're going to start streamlining this process once we get into the next section. So I hope you all stick with me, and I hope that you all enjoyed this lesson, and I will see you all for the next one.